one of the things of tangent planes that's the most important, really why we study them a lot of times, is because they form a nice linear approximation to the curve. This is very similar to what you did in Calculus 1, where if you take your x squared here, your x squared function, then your tangent plane approximates it. It's a good linear approximation. It's a line approximation of the curve. So notice that instead of using x squared in this little interval here, we can use, arguably, we can use the tangent line approximation to it instead. I got that from just doing some calculus. I have f of x is x squared, took the derivative, got 2x. I plug in my point c squared into the derivative. This gives me the slope that I'm going to put here. I use my point slope formula, y minus c squared equals 2c times x minus c. I did the math and I got y equals 2cx minus c squared. So that's how I got this down here. That's my tangent. And so you can see for yourself, you can make this yourself, create a function, and then do the math to get the associated tangent line at any point on the function. All right. Down here, the tangent line is not a good approximation because even if you zoom in, sort of when you zoom in, you see that it's not that great of an approximation for very long. Okay. So the similar idea is with this tangent plane. So I invite you to figure out how I got from z equals e to the x minus y, which is this, it's this curved surface here. It's this curved surface here, and then I picked a point 2, 2, 1 because it's nice to plug in, and I got this tangent plane in blue here that you see. So see if you can get that on your own. Then what I did was I picked a point c, d, e to the c minus d, and if you notice, as c moves in the x direction, the point moves, and as d moves in the y direction, it moves as well, right, in the y direction. So I did the same process, but with, in order to get this tangent plane here, I did the same process as I would in Cal 1, but with the new formula from Calculus 3. So here's my surface here, z equals e to the x minus y. I picked the point c, d, e to the c minus d, plug in c and d, get e to the c minus d. I took the first derivative with respect to x, the derivative with respect to y. I got my slopes in the x and the y directions, and then I did the math using the formula, and I got this tangent plane down here. So notice that's what's down here as well. So the tangent plane moves with it as we move c and d. And if you notice, the tangent plane is a pretty good approximation, not too bad actually, as we zoom in. It's even better though if we go flatter to the flatter part of this graph. So I invite you to experiment with this sum using your own functions here and your own points.